Alright, welcome to part 2 of creating data structures that are beautiful, handmade genius in C. And I left off last time just as I was getting into how insert vectors worked. So to recap over here, we're making vectors that are everywhere in programming. Probably easily one of the most common data structures you'll run into. And we're just going to implement our own in C. They're just basically at their heart resizable arrays. And what we're doing over here is we're trying to get a function to insert some bytes of data to be precise, inserting len bytes of data at index of the vector. And the vector is indexed by bytes because we're not making any assumptions about what kind of types this is holding, so they'll just have to convert to and from bytes. So that's about right where we are. And the first thing that we've done is we've just increased the logical size of this vector. And the next thing that we're going to do to it is we're going to have to move our memory backwards, as in farther along the array so it doesn't get overridden by the new space that we're going to add in. So our source for the data that we're going to start moving is going to be called, I'm going to call it a circ. And we're going to index this via bytes. This is just a byte. It's an unsigned integer type that is 8 bits long, so 1 byte. Really simple. And this is called our circ. And we're going to use the vector, the function we created last time to index it because we already wrote it, so we might as well use it. And so what we're going to tell it is we're going to tell it to get the, sorry, not vector, we named it v, didn't we? We're going to tell it to get the indexed byte, get the memory location of the indexed byte. And that's exactly what it's doing for us. We're getting the memory location of the indexed byte. And this way we don't have to do any more pointer arithmetic because it can be a bit dangerous sometimes. And we're going to place it farther back, so placing it the length of bytes after the index that we've mentioned. So plus len. So this gets us, so this is where we're going to start taking our data from, and this is how much data we're going to take. And of course, this is how much data we're going to copy. Now, there are a few, we could of course write our own for loop, but C kindly already provides a function inside the standard library called memcopy. And this is automatically included when you decide to include string.h. So string.h contains memcopy, memmove, and a bunch of other string related and memory related functions. So that's what we're going to use. So make sure to include this. And so the next step, there are two functions inside C that are commonly used to move memory: memcopy and memmove. Memcopy is basically the same thing as memmove, except memcopy does not work when you have memory that overlaps another memory, and memmove does. So we're going to use memmove, even though memmove might be a bit slower than memcopy, because our data is most definitely overlapping. Like if we had 100 bytes and we inserted halfway through, 49 of those bytes would overlap. So we definitely care about overlapping memory. So that's why we're going to use memmove over memcopy. But if your short's not going to overlap, use memcopy because it's faster. So the function looks like this: destination, source, and how many bytes you want. So len bytes, obviously. And memmove is a tad weird because it always puts the destination first. Same deal with memcopy. Memcopy, memmove, destination first, source next, and length last. So they both work inside pretty much the same way. Now that we've copied over our memory, there's only a little bit left to do. So one thing that we've done is, if you'll follow the example, is we've basically taken our memory chunk, we've divided it in two, and now we've moved the second half over like len bytes, right? So then we have this little space in the middle. That's our inserted space. And inside that, we're gonna set everything to 0, so give it a fresh, clean slate to the next person, right? Like, you wouldn't give someone a dirty plate or something like that. No, just unacceptable. In this case, you gotta like clean it up. So what we're gonna do is we're gonna set every single byte in there to 0, and we're gonna use a nice little function from the same general thing called memset. So it's pretty simple. All memset takes is it takes the memory location, which is circ. It takes the byte we're gonna copy over, and we're gonna copy it or paste over it with zeros, and then the length of the bytes, and the length of the bytes is predictably len. So that's done. And once we've done this, we can basically return this. We're returning circ, which is now a beautifully len bytes of zeros that's been inserted between index and the rest of it, right? And now the last bit is remove. Remove basically works the exact opposite of vector. It's just removes data. Well, to be specific, removes len bytes of data at location index at vector b. It's not gonna return anything because there's nothing to return. We just deleted that data that theoretically we could return, but we can't because it's technically not owned by the vector anymore. So we'll avoid that. Remove vector. So of course we're removing it at index, and we're going to remove the len bytes of it. So the first bit, of course, is to check if we're inbounds or out of bounds. And the thing is over here that we have to kind of ensure that we're not moving too much, because the real threat is we could be close to the end of the vector, like say the vector is 10 bytes long and the index is 9, and we want to remove 12 bytes from the end. We don't have that much space to remove all of that, right? We don't even own the next 11 bytes. So that's something we gotta be careful for, and that's what we're gonna do a little if statement to check for that edge case. If the index, sorry, not the index, if the length is greater than however much space we have left, which is vector.length, sorry, not vector, v.length minus len, right? That's telling us, not len, sorry, index. That's telling us that hey, there's really not enough space for you to even take this out, you know. And that's what we're gonna tell the user. Not enough room at end of array to remove this many bytes, and we're gonna exit with the failure. So next step, it's pretty much exactly the same but in reverse, right? So the idea is we've got an index and we've got a len of space removed. So what we're going to do is we're going to take from the len, right? We're going to take from the len, and we're going to take all the stuff from the len to the end, and we're going to copy that over right here to index, right? So we're overwriting all the space between index plus len and index with all the stuff that was past index plus len. It's pretty straightforward, right? So the first thing we've got to do, of course, is shrink the size of the vector. So it's vector just v.length minus equals len. So that just shrunk the logical size of the vector a little bit. The next step, we can just straight up copy over here because it's just the same, except the source and destination are kind of reversed. So let's do that. We're just going to copy from over there, and we're switching the source and destination. This thing, now our destination. Dest for short. This thing is our source because copying from farther back on the array, and we're putting it closer to the array. And our mem move is the same too, because we're moving from destination to source as is convention. And the good thing is we don't actually have to mem set anything, because there's nothing left. We've just shrunk the size of the array. They can't be accessing anything else of the array because it's supposed to be garbage anyway. So they shouldn't even be accessing it, so we don't have to worry about it. And that actually speeds it up a bit, not noticeably. But that's the last thing we have to do, and that's it. except for one last thing. We said over here we were gonna learn how to resize the vector at some point, right? And that's what we gotta do. We gotta figure out how to resize the vector, and then we'll be done. So we're gonna create a function that's only meant for use inside of the vector. Only meant for use inside of the vector. And so to do that, we basically say static. Static means it's only usable inside the file. So static resize vector, and it's going to be a void function because we're not going to return anything. We're just modifying some facts about the vector, like its capacity, because that's what we're changing. We're changing its capacity. And of course, we gotta take in a new. What is it? We're gonna take in some. Whatever the new size has to be, or rather, how many bytes they want to insert. So, size t bytes to insert, right? And that'll tell us how many bytes they want to insert, and we'll make we'll figure out how much to expand the vector from there. And to do this, we're going to use a function called realloc. So realloc is kind of like a cousin of malloc and calloc. They're all allocation functions that have been provided by the C standard library to us. Except realloc takes a portion of allocated memory that's already like len bytes and can resize that portion of memory to ask for more or less. And so this is an incredibly helpful function in this case, because it means that we don't have to create a new one and copy everything over. We can just reallocate how much memory we have. And to do this, it's really simple. It's as simple as realloc v data and however many bytes we want. So you could just say, v data capacity plus bytes to insert, right? And this might actually work, as a matter of fact. This is a valid reallocation function. And over here, all we'd say is and that's it. However, the thing is, reallocation and allocation are actually pretty expensive functions when you look at the grand scale thing. When I say expensive, I don't mean cost-wise expensive. I mean time-wise expensive. But in the end, they're the same thing because money is time. When you deal with these kind of stuff, you're wasting microseconds. That's right, microseconds of your life you could have been doing something else. And that's bad because when you end up using these in practical usage, you're usually doing a lot of inserting and a lot of de-inserting and freeing, you know? So these things undergo very heavy use, especially in like kernels, video games. They're always doing stuff like this, and you don't want to slow down even a microsecond. Over there, like nanoseconds count, you know? So what we're going to do is we're going to be intellectual and minimize the amount of reallocation that this thing has to do, while still making sure that we're not consuming insane amounts of memory. And that's where the load factor I mentioned previously comes in, right? The load factor basically tells us how much to expand each time. It tells us, hey, we want to add, we're going to rescale it by this much. So I'm just going to say v dot load factor times v dot capacity times byte to insert. The reason I'm doing v dot capacity not v dot length is solely because bigger is better. Like, the less allocation we have to do, the better, you know? I mean, realistically speaking, we might be using a bit of excess memory. It's just ridiculous how much memory we've got. And I think we might as well reuse that. Or use that to the best of our abilities. So, what I just did was since load factor is a float, right? We're gonna multiply v dot capacity plus bytes to insert by our load factor and then cast that to a size t so realloc can handle it. And with that, there's one last bit we have to do. We just have to say, size t new capacity. Rather, we don't have to do that. We just say v capacity is equal to we're just gonna copy that right there because I have to set that anyway, right? And we just say v.capacity. Boom, we're done. And with that, we basically gathered the 5 infinity stones in the manner of speaking, right? But we probably want to test this out, like how are we doing so far? So I'm gonna attempt, emphasis on attempt, to compile this this monstrosity, so to speak. It's not really a monstrosity, it's a beautiful creation, handmade, crafted, you know, data structures, whatever. So here we are, vector.c, cc vector.c. Oh, it's an error. So what it's telling us is there's an undefined reference to main. And it makes sense because in C, every single program needs a main, a point to start. And that's what we're gonna add. We're gonna add a main function. We're gonna do all the testing of our vector library. So let's add it in. Int main. And it compiles, but it doesn't do anything. So what it compiles to is a little something called a.out, right? And this when we run a.out, it doesn't do anything because it's empty. So let's get started with a little bit of test suite. I'm just gonna say vector v, right? And we declared a new variable. Right? We haven't initialized it. That's what init vector is for. And we're gonna just give it a pointer to the vector and v. And now we've initialized the vector. I'm gonna free vector and v. And yeah, and we're gonna do some stuff in between this. So let's think about it. I'm gonna test out all of our vectors. So I'm gonna, of course, the vector starts out with 0, so we might as well insert some stuff. We're gonna insert vector v. The only index is 0, and let me insert 100 bytes. And I'm gonna set each of these bytes from 1 to 0. This should work, right? And then we're gonna go through it again and print it out to see that it really worked. Oh, actually no, let's do some removes before then. Let's test out the other feature. Let's insert a little bit more. So let's insert at 23. And let's insert 10 bytes. And let's remove some vector. Let's start removing at 53, 10 bytes. And then let's print everything out. Just v dot length, not v arrow length, because we're not dealing with a pointer. So let's and whoop. We'll be right back. Alright, so yes, we had a bit of a boo-boo over there, but it was worse than I thought it was. You might have thought, oh, it's just a simple bug. Well, guess what? It was a memory corruption error. We had been the example code provided, and not only did it not fail to function, it corrupted my entire heap. And I was like, Chief. But then I spent 45 minutes of my Tuesday debugging that thing, and I tracked it down to its source. Can you guess the problem with this line of code right here? It's kind of subtle actually. The mem move, we're not actually gonna move mem bytes over here, are we? What we're gonna move is all the bytes from index to the old length of the vector, like the length of the vector before we expanded it. So we're taking all that stuff and we're gonna move it, and that gets represented not by len, but by vector. Sorry, not vector. There's no vector around here. It's v.length minus lock minus lock plus len. Not lock, index plus len, right? Because it's, I was thinking about location wise, but not really. So you see, what happened was it wrote too much or too little, and something it did corrupted the malloc's special bytes that it put to signal to end. And in doing so, without getting too abstract, the entire thing got corrupted, and I didn't notice until the very end because it looked like it was working fine, but it wasn't working fine. It was a menace to society. So here we have our thingy, right? We're basically moving from the length, the old length, to the new index, and that's how much space we've got. That's the idea. From the index to the old length, and we're moving that all the way back. And I made a similar boo-boo over here, and either one of these could have caused the issue. Probably it was both of them. Nope, we're not moving len bytes. We're moving all the way to the length of the vector bytes. V dot length minus index. That's how many bytes we gotta move all the way back. Once we do this, we've actually solved our issue. Even though it's giving us an error at printf, that's only because of the same issue that we were facing. The entire heap was corrupted, and that's why the index came, the error came at a weird place when we were trying to print. But really, the issue was all the way up there. And most of all, remember to change these lines in your code if you're following along, because this really pranked me over here. Not gonna lie. Alright, so let's see. Will it work this time? Man versus machine. When I say cc vector.c, what that means is c compiler vector.c. And boom, it worked. It's just, I'm just speechless because I have so much emotion in my heart right now. I don't know what to say. But yeah, the reason it says 1 over here is because I just did a printf1 just as a test and failed over there as well. So I figured that's when I realized something was wrong, because like if it's not printing 1, then we got issues, and we did have issues. So that's why it says 1. It should really say 0, 0, 0. So let me just see. Now that's proper. So see, let's take a look. It's going good so far, right? But then, hold up. This is the place where we inserted 10 bytes of info, right? And so we're 10 bytes behind because we just inserted that. It's like 23 and carries on from where it left off, right? And then, boom, over here it's 39.49, and then over here it's like, over here it was like 52.42. Now it's 53.53 because that's where we removed 10 bytes to catch it up to speed, because we insert 10 bytes, we remove 10 bytes, now we're back up to equivalency. And that's how it ends. So, congratulations, you just learned how to make your C vector. So, I've posted a neatened, better version of the code with a few more features up on GitHub, in github.com/benpali/cvec. So you can see it over there. And that's also where I renamed some variables, I added a few comments, and I cleaned up the code. But in a nutshell, 2 things you can learn. Vectors, pretty dank. What's not so dank is dying on the inside because your memory was corrupted. That's about it. Thanks for listening. Hope you enjoyed.